Going on now to topic 3 of chapter 4. We skip topic 2, modeling with exponential functions. The list of objectives, again, we'll be going through these as we go along. Now, one of the basic differences between linear functions that we speak about below, where we have a straight line in a sense, exponential is a curved line that starts off slow and then shoots up. Now, in example 1, and you want to include that in your notes, we're wondering, is the situation an example of linear growth? That would be a straight line, or exponential growth where it would develop in a curve. So here we have a test tube contains a certain type of cell that triples every hour. And then B, test tube contains a different type of cells that increases by 3 cells every hour. So think about that. Now, number 1, if you start to plot that, it's going to be a curve that looks like so. But B is going to be a straight line growth here. I didn't draw too straight a line. This is a curved line. This is a straight line. All right, let's take a look at this. So as we look at number 1, test tube 1, we start off with 1, then we go to 3, then we go to 9, then we go to 27. And we describe this kind of growth as exponential growth. While as we look at test tube 2, we're adding 3 each hour. So we have 1, 4, 7, 10. Notice this growth is so much slower or less and results in a straight line, while the previous one results in that curved exponential kind of growth. And for number 2, we want to add this function statement. And this is the function symbol, f of x, equals 3 to the x power. So x would be the number of hours. This is exponential growth. And the growth in tube 2 now, its function form, here they're using another letter, which is okay. They often use F, but you could use another letter. And that equals 3x plus 1. Okay, so notice that this is, if we change this function symbol to a y, we have our old friend, y equals mx plus b. And we knew this was a straight line. All right, let's continue. Now, this next one, again, it's all part of our background information that option 1, a king deposits the same amount of money, $50,000 into an account each day. Okay? Now, this would be linear, and the equation for this would be this. L of x is 50,000 times x, which is the number of days. Now, option 2, the account starts with just 2 pennies, and the amount of money is doubled each day. Now, this is modeled by the function of e is such that you have 2 times 1 penny, that's 2, but it doubles. The exponent is the variable. So let's just take a look at this. Now in table 1, we're going to double the pennies. and you don't have to write this down, but just try to imagine the concept that after 10 days, you have $10.24. And for the $50,000 being added each day, you end up with $500,000, 500,000. But note this, how about after 30 days? And this is just 2 pennies a day, doubling. After 30 days, you end up with $10,737,418.24. So again, option 1 shows linear growth, while option 2 shows exponential growth. Notice this linear is a straight line, and you get this type of curve for exponential growth. All right, let's go on. Now, as we continue background information, I want you to sketch a little T-chart in your notebook, and we're going to put the value here 1. Well, first 0, then 1, 2, and then we'll put in there a -1. And then we're going to use this function that they're giving us, f of x is equal to 3 to the x power. So remember, f of x can be substituted with a y. So this is our y. We could put here f of x too if we wanted. Now, if x is 0, this x here is 0, 3 to the 0 power, or anything to the 0 power, is 1. Now, 3 to the first power is 3, and 3 to the second power is 9. Now, getting back to our study of exponents, negative exponents, what will be 3 to the -1 power? Well, we said that was just take that down to the denominator, and that becomes 1 over 3 to the first, or 1/3. So now you want to sketch a graph in your notes, and we're going to need up to, let's say, 9 or so up here. And we're going to plot these points. So if x is 0, y is 1, we got a point right there. If x is 1, y is 3, so we go up here. If x is 2, y is 9, so we go right up there. Now, if x is a -1, y is 1/3, and we get right about there. So we actually have enough points to sort of sketch this graph. So this now is so typical of exponential growth. Now remember the standard form, and you should write this down too. F of x equals b to the x power. This would be the standard form, where this is your y value in a sense that we're expanding. Okay, let's continue. And again, just for comparison, this equation would be y equals 3x plus 1, which is in slope-intercept form. There's your 1 over 1 up 3, and it gives you a straight line. So again, we're spending a lot of time building background, comparing linear growth to exponential growth. Now, for example 2, we're going to graph the function f of x is equal to our base 2 to the x power. And we're going to go to the whiteboard for this, and we want you to sketch it in your notes as well. Now, shortly, we'll see a really well-made graph, but I want you to get the practice now of sketching this and doing this in your class notebook. So, if x is 0, 2 to the 0 power is anything to the 0 power except 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. Now, 2 to the negative 1 that we had before, just bring that down, it becomes 2 to the first in the denominator, which is 1/2. And 2 to the negative 2, again, that becomes 1 over 2 to the second, which is 4. And then 2 to the negative 3 is 1 over 2 to the third, which is 1/8. Now, I don't know if you're picking up on this, but if you have a value to a whole number, then when it's a negative exponent, it just becomes the reciprocal of this. So now let's do the plotting. So if x is 0 right there, our y value is going to be 1. If x is 1, our y value is 2. If x is 2, our y value is 4. If x is 3, our y value is 8. So we get an idea of what the curve, I guess this could be over a little bit more this way too. Come think of it. Now let's do the negative values. If it's negative 1, x is negative 1, it's 1/2. Negative 2, 1/4. Negative 3, 1/8. And these get closer and closer, but let's take a moment to sketch this. So it's coming like so, going up here. Got to get into a better position here. And of course, this goes on to infinity in this direction and infinity in that direction. So one of the things we like also to add here is the domain. And those would be the x values that we want to write in interval notation. Well, we say it's going to end up here in negative infinity. That's where it's going or coming from. And then eventually this goes out this way too, way over to positive infinity. Now the range deals with our y values. Now it gets closer and closer to the x-axis, where the y value right there is actually 0. And the x-axis is a special name that I will give you in just a few moments. But therefore, the y values never reach the 0. So we use a parenthesis for 0, and this goes to positive infinity. Now, what do we call a line that something gets very close to but never reaches? Well, we call that, and this is the word I'd like you to write in your notes, an asymptote. And the asymptote of this graph happens to be the x-axis. Now, what direction does the x-axis lie? Well, it's horizontal, so we call this a horizontal.
the horizontal asymptote when it's in this direction. Later in one of our other units, we'll talk about a vertical asymptote, which is the y-axis, but not yet. So a number of things we've done here. All right, let's go and look at the nice graph they're going to give us.
So just look at this. We see a beautiful curve here. Notice there's an infinite number of points on this line, and it shows typical exponential growth, where we stick a coefficient in front of our base. So write this down as exponential growth function. Now, as long as our exponent is positive, we get exponential growth. If our exponent is negative, then we're going to get decay. So again, a general background item. Now, for this example, example 3, write that down. You're going to note that we're going to start with 100 bacteria. So y sub O is the original amount. That's that constant there that we started off with, the coefficient. Now it's going to increase 2 at this exponent t. And here they're giving us 12 hours. So we're going to convert this now into this formula. Y equals 100, that's what you're starting with, times 2 to the 12th power. And that's what you have. So in 12 hours, if you started with 100, you're going to end up close to 500,000. Wow. Write this down. This is an example of bacterial growth, and bacterial growth is exponential. And this shoots up like that 2 cents that we had in an earlier background item. Now, as we look at this example of decay, if your value is greater than 0 but less than 1, that is some sort of decimal fraction less than 1, this will give you decay, and it's the same formula. It's just that your base here is greater than 0 but less than 1. All right, let's look at an example of this. In example 4, they're talking about a computer that was purchased originally for this, but there is depreciation by 40%. Then it would retain only 60% of its value. And if this goes on for a period of time, you can see the curve will start to look like this. So instead of looking like that, this shows depreciation. So for example 4, we'll set it up. And again, it's a similar formula right there. The initial amount is 2,750. It's going to depreciate 40%, so it retains 60% of its value. But after 4 years, what would it be worth? So you put that in your calculator and you get $356.40. So again, you want to have an example, for example 4, of exponential decay and the rationale for it. All right, continuing, we have something we may have mentioned earlier in the course, and that is the letter E. Now, this letter E is named after or is related to a very famous mathematician called Euler. I want you to write this down too. So you might think of it pronounced a different way, but the U is pronounced as an O in the German. So Theodore Euler would not be the correct way. It's Euler. All right. I said it the wrong way. All right. And he is associated with this number E. And what is E? Well, it's an irrational number and has this approximate value. So take a moment as a little quirk to write this down. Now remember the three dots are the ellipses. That indicates this irregular pattern goes on and never ends, what makes the letter E irrational. Now, another thing I'd like you to note about E is that it is sometimes called the natural base. You might say, are there other bases? Well, the base we use in our mathematical calculations in general is base 10, which is the common base. Okay, now we also want to look at what is called continuous interest, and I'll move it up for that. And we want you to write this in your notes. So continuous compound interest. Now I should have a little link up here which illustrates that by another video that I've seen on YouTube, and I'd like to have you watch that if you have the time. It goes over this in some detail. So what is the continuous compound interest formula? Well, it's A, which is for the future amount, is equal to the principal times Euler's E, and then the exponents are the rate times the time. So this is continuous interest formula. And we're going to look at it. Now, for example 5 here, we want to take this information and put it in the formula. So we need to read it carefully. So we don't know the future amount. Now the principal is 10,000. We need to find where on our calculator is the letter E. And then in some cases we have to put a caret there, or sometimes it's built in. So you have to be sure you know how to use your instrument. And then the rate is going to be 0.9, so that goes 0.009, converting that to its decimal fraction. And this is going to be times the time, which is going to be 5 years. So just carefully putting that into your calculator, and they want you to round to 2 decimal places, you get $10,460.28. Again, try that so you're able to know that your instrument will give you this type of answer once you put this data into your calculator. All right, this winds up lesson 4.3, and we should expect a quiz and hopefully have some good notes.